Okay, let's unpack this. Have you ever really stopped to think how these huge networks manage everything? Cloud data centers, massive company campuses,
Hmm.
keeping everything connected, flexible, moving smoothly without, hitting a wall. The scale is just incredible now.
It really is.
So today we're doing a deep dive into the architecture that actually makes that possible. It's called BGP EVPN VXLAN.
Quite a mouthful.
Yeah, it's a lot of acronyms, I know, but honestly, it's a pretty elegant solution, really crucial for today's networks.
Absolutely. And our mission today really is to kind of pull back the curtain on this, demystify it a bit.
Right.
We'll look at how it evolved, the problems it solves, the core ideas, basically helping you understand not just what it is, but why it matters so much. It's sort of the backbone for the kind of networks we just expect now.
Okay, so where should we start? Maybe looking back.
Yeah, the before times, as you called them.
Right. For ages, VLANs were, well, they were the standard for chopping up networks, weren't they?
They served a purpose.
But they had some pretty serious downsides. I mean, that 4094 VLAN limit, anyone running a big network felt that pinch.
Oh, definitely. For large IT shops, cloud providers, that was like an iron ceiling. Really limited how big or complex things could get.
And then there was spanning tree protocol, STP, for stopping loops. Necessary, yeah, but it also really constrained network design resilience.
It did. And what's interesting there is, while VLANs worked for a long time, the way they were designed, especially with things like STP, it just created bottlenecks. They just couldn't scale up. Not for what modern campuses or data centers needed. It was like trying to run a high-speed train network on old local tracks. Just wasn't going to fly.
So something new was needed badly.
Exactly. And that's where VXLAN sort of stepped onto the scene, a really key innovation.
Yeah.
It was specifically designed to get around those VLAN and STP problems, still offering layer 2 services, but with way more flexibility.
So how does it work functionally?
Think of it like taking your normal layer 2 data frame and just wrapping it up, encapsulating it inside a standard layer 3 UDP packet.
Ah, like putting a letter in a new, faster envelope.
Pretty much. And sending it over your existing routed layer 3 network. The underlying network doesn't need to know about the original layer 2 stuff inside.
Okay, that makes sense. But you said it wasn't the complete picture.
Right. That's the kicker. VXLAN by itself, initially anyway, it used this thing called flood and learn to find where hosts were.
Flood and learn. Sounds noisy.
It was. Imagine a device needing to find another one. It basically had to shout across the whole network, hey, where are you? Lots of broadcast traffic.
Right, okay. Not scalable.
Not at all for large networks.
Yeah.
So VXLAN was this powerful data plane, the part that moves the data, but it needed a brain, a smart control plane to manage it all efficiently.
Okay, so this is where it gets really interesting then. To get that scalability, that intelligence, VXLAN needed this control plane.
Precisely.
And that's where EVPN comes in. Powered by MPBGP.
Exactly. EVPN stands for Ethernet VPN, and it basically extends BGP, Border Gateway Protocol, the thing that runs the internet.
Right.
EVPN lets BGP carry both layer 2 IP address info and layer 3 IP address info at the same time. And it's all built on standard specs, so different vendors can work together.
So EVPN is the brain telling VXLAN, the brawn, what to do.
That's a great way to put it. The synergy is key. EVPN handles the control plane intelligence, distributing the AMI and IP info efficiently. VXLAN handles the data plane, wrapping up the packets.
Okay.
Together, you get this BGP EVPN VXLAN fabric, and that combo dramatically cuts down on that old flood and learn noise. It optimizes everything, routing, switching, much smarter.
The brain and brawn working together. I like that.
Yeah.
So, okay, elegant design. Sounds clever. But let's talk benefits.
Yeah.
What are the real-world upsides for, the people actually running these networks? What makes it a game changer?
Yeah, good question. It really boils down to 3 main advantages, big ones.
Okay.
First, scalability, like massive scalability. VXLAN supports up to 16 million separate tenant networks.
16 million. Wow. Compared to 4,000.
Exactly. Think about a huge cloud provider. They need to support maybe millions of customers, each needing their own isolated, secure network. VXLAN makes that possible. It just shatters that old VLAN ceiling.
Okay, that's huge. What's number 2?
Second, flexibility. Your workloads, your servers, your VMs, they can be placed anywhere in the fabric. Doesn't matter physically where they are.
How does that work?
Traffic separation uses those VXLAN network identifiers, the VNIs we'll talk more about. So you can have workloads spread across different racks, different rooms, even different buildings. But logically, they're still in the same network segment.
Like virtual neighbors, even if they're physically far apart.
Exactly. It's like having offices anywhere, but they all feel like they're on the same floor.
Nice. And the third benefit?
Third, mobility. This is a big one for virtualized environments. VMs can move from one physical server to another.
Live migration, yeah.
Right, even across different parts of the data center. And you don't need to manually reconfigure the network switches every time.
Why not?
Because as long as the VM stays within the same logical VXLAN segment, it keeps its identity, its VNI. The network control plane, the EVPN part, just automatically figures out its new physical location and updates things dynamically. Seamless moves.
Okay, scalability, flexibility, mobility, those are definitely major advantages.
Oh.
All right, so we get the why. Now, let's dig into the how. Let's unpack the architecture itself, the components, the terms. We hear underlay and overlay a lot. What's the difference there?
Good place to start. So the underlay network, think of that as the physical foundation. It's your actual layer 3 network. Cables, routers, switches, the hardware that provides the transport. It's the highway system.
Okay, the physical roads.
Exactly. Then the overlay network is the virtual network you build on top of that highway. This is where VXLAN lives. Your original data packets get wrapped in that VXLAN header at the starting edge.
Encapsulated.
Right, encapsulated. Then they travel across the underlay. The intermediate routers don't even know what's inside the wrapper, and then they get unwrapped, decapsulated at the destination edge.
Like shipping containers on the highway. The road doesn't care what's inside the container.
Perfect analogy.
And you mentioned edge devices. These are the ones doing the wrapping and unwrapping.
Absolutely crucial. Those are your VTPs, virtual tunnel endpoints. They sit right at the edge of the VXLAN network.
Good.
They're responsible for creating the tunnels, doing that MPI and UDP encapsulation, sending the packet into the underlay, and then decapsulating it when it arrives for another endpoint.
So what do they look like? Are they special hardware?
Typically, they're switches. A VTIP usually has a normal switch interface connecting to the local devices, the servers, or whatever, and then an IP interface connecting to that layer 3 underlay transport network. In modern setups, you'll often hear VTIPs called leaf switches.
Leaf switches, okay. And with potentially 16 million of these virtual overlay networks, how does the system keep track? How does it know which packet belongs to which virtual network?
That's the VXLAN network identifier. It's a 24-bit number.
24 bits, okay. That gives you the 16 million possibilities.
Exactly. Each unique VNI identifies a specific VXLAN segment or virtual network. So packets for customer A get VNI 1001, packets for customer B get VNI 1002, and so on. That's how you get that massive multi-tenancy and separation. It's a huge leap from the 12 bits used for VXLAN.
Right, makes sense. Now, for the physical layout, especially in data centers, we hear spine leaf all the time. How does that fit with VTEPs and VXLAN?
Yeah, spine leaf is the standard topology now for these fabrics. It's a two-tier design. You have leaf switches at the edge.
Those are the VTEPs we just talked about.
Often, yes. The leaf switches connect directly to your servers, storage, other endpoints. They handle the VXLAN decapsulation, the VTEP functions.
Okay, and the spine.
The spine switches form the backbone. They interconnect all the leaf switches. Think of it like every leaf connects to every spine.
A full mesh between leaves and spines.
Sort of, yeah. The key is that spine switches provide high-speed transport between the leaves. They usually just do layer 3 routing based on the VTIP addresses in the outer header. They don't typically need to know about the end hosts or the VNIs. They just provide fast, redundant paths.
So leaf talk to hosts and do VXLAN, spines talk to leaves and just route fast.
That's the basic idea. And then you'll also have border leaf or maybe border spine switches. Their job is to connect the entire VXLAN fabric to the outside world, other traditional networks, the internet, etc. They're the on-ramps and off-ramps for your fabric.
Got it. Okay. Physical layout makes sense. But you said earlier EVPN was the brain that stopped the old flood and learn problem. How does that EVPN control plane actually figure out where everything is? How does it distribute that information?
Right. This is the core of the intelligence, the EVPN control plane mechanics. Instead of flooding ARP requests everywhere,
Right.
EVPN uses MP BGP, multi-protocol BGP. It uses BGP updates to distribute all the necessary reachability information proactively. This includes the MSE addresses of endpoints, their corresponding IP addresses, which VTTP they're connected to, essentially the full mapping.
So before a packet even needs to be sent, the VTPs already know where the destination is.
Exactly. Each VTTP builds this local database, this mapping table, based on the information it receives via BGP from other VTPs. So when a packet arrives destined for a known MS or IP, the VTT just looks it up, finds the right destination VTT, encapsulates the packet, and sends it directly. No flooding needed for known destinations.
Much more efficient.
Massively. Now, within EVPN, there are a few other concepts. You have an EVPN instance, or EVI. Think of this like a VRF, but for layer 2. It creates a separate, isolated MASH forwarding table on the VTP for each tenant or VPN. Total separation.
So like a Membassy VRF.
Exactly. Sometimes it's called that. Then you have an Ethernet segment. That's basically the link or set of links connecting a host or device to one or more VTTs. It gets a unique ID called an Ethernet Segment Identifier, or ESI.
Why is the ESI important?
It's key for multi-homing. If a server, for example, is connected to 2 different leaf switches for redundancy, both connections will share the same ESI. This tells the network, hey, these 2 paths lead to the same logical endpoint. Helps prevent loops and manage failover.
Okay. And I think you mentioned different route types in EVPN.
Yes, there are several defined route types in the standards. For today, the most important ones to maybe know are route type 2 and route type 3.
Okay.
Route type 2 is the main one. It advertises your endpoint MHAS and IP addresses. Basically, host X with MHAS with MAY and IPZ is connected to me.
The core reachability info.
Precisely. Route type 3 is used for optimizing multicast traffic, basically telling other VTPs which ones are interested in receiving certain multicast streams. Helps avoid unnecessary multicast flooding, too.
And how is all this information controlled, especially with multiple tenants? How do you ensure tenant A's routes don't leak to tenant B?
That's where route targets RTs come in. These are special attributes, kind of like tags, attached to the EVPN routes within BGP. Each VTP, for each tenant network, each EVI or VRF, is configured with specific RTs it will export, attached to routes it advertises, and import, except from routes it receives. So tenant A's VTPs export RTA and import OTA. Tenant B's VTPs export and import RTB. They simply won't import each other's routes. It provides really strong isolation.
So the RTs act like filters, controlling the flow of routing information between tenants.
Exactly. It's fundamental to secure multi-tenancy. And speaking of robustness, we touched on EVPN multi-homing with the ESI. This is a huge feature.
Connecting a device to multiple leaves, right?
Right, for redundancy. If one leaf switch fails, or the link fails, the device still has connectivity through the other leaf. It can work in single active mode, where only one link is forwarding at a time, or all active, where both links can be used simultaneously for load balancing. Big improvement over older methods like STP for resiliency, less downtime, happier users.
Definitely sounds like it. Okay, so we have layer 2 traffic moving around using VNIs, layer 3 info shared via BGP. What about routing between different virtual networks, or connecting to things outside the VXLAN fabric?
Good question. That brings us to integrated routing and bridging, IRB, and VXLAN gateways.
IRB sounds familiar from traditional networking.
It is, conceptually. IRB allows a single interface, in this case on the VTEP, to act as both a layer 2 switched interface for traffic within the same VLAN VNI and a layer 3 routed interface for traffic going between different VLANs, VNIs, or subnets.
So the VTEP itself can be the default gateway for the hosts connected to it.
Exactly. The leaf switch often acts as the VXLAN gateway. It handles forwarding traffic within a VXLAN segment, layer 2 bridging, and routing traffic between different VXLAN segments or between a VXLAN segment and a traditional non-VXLAN network, layer 3 routing.
Okay, so the gateway function is often right there at the leaf VTEP.
Very often, yes. Especially in distributed gateway models. This keeps traffic local and efficient. Now, to support this routing, we distinguish between layer 2 VNIs, L2 VNIs, and layer 3 VNIs, L3 VNIs.
What's the difference?
An L2 VNI maps directly to a broadcast domain, like a traditional VLAN, extending it across the fabric. It's for keeping hosts within the same logical layer 2 segment connected. An L3 VNI is associated with a VRF, a virtual routing and forwarding instance. It's used specifically for routing between different subnets or different L2 VNIs. Each tenant typically gets its own L3 VNI tied to its VRF for layer 3 isolation.
So L2 VNI for within a subnet, L3 VNI for between subnets tied to VRFs for multi-tenancy.
Got it. You got it. And finally, addressing that mobility point again. What happens when a VM moves and its MC address suddenly appears on a different VTEP?
Yeah, how does a network update quickly?
That's MSC mobility and IP mobility, too. The BGP EVPN control plane handles this elegantly. When a manifest moves, the new VTIP it connects to advertises the MY reachability via BGP. Crucially, these updates include a sequence number.
A sequence number?
Yes. If multiple VTTs somehow advertise the same MC, the network uses the highest sequence number to determine the most recent and therefore correct location. The old VTT also withdraws its route for that MS. It resolves potential conflicts and ensures everyone knows the latest location very quickly.
Why?
And importantly, MSE addresses learned via the EVPN control plane, these remote MAs aren't subject to the normal MNIS aging timer you find in traditional switches.
Because the control plane is actively maintaining their state.
Precisely. This is critical for supporting mobility. You don't want the network to forget where a VM is just because it hasn't sent traffic for a few minutes. The system also has mechanisms to detect and flag duplicate MSC or IP addresses, which can cause serious problems. It helps maintain network integrity.
Wow, okay. That's a lot of intelligence built in. It sounds incredibly powerful, incredibly robust. But are there ways to fine-tune it, make it even more efficient, especially in really, really busy networks?
Absolutely. Optimization is always key at scale. One really important one is ARP suppression.
ARP suppression. Okay, what's that tackle?
Think about ARP address resolution protocol. Who has this IP tell this MAC? In a large layer 2 segment, even one extended by VXLAN, that can generate a ton of broadcast traffic, just constant chatter.
Yeah, ARP swarms are no fun.
Exactly. So ARP suppression is a way to quiet that down. The local edge device, the VTE pleaf that the requesting host is connected to, acts as an ARP proxy.
Ow.
If the VTEP already knows the XT address for the requested IP because it learned it via EVPN, it just replies directly to the ARP request itself. It doesn't need to flood the ARP request across the entire VXLAN fabric.
Yeah. So it intercepts the ARP request and answers locally if it can.
Precisely. It suppresses the need to broadcast the ARP everywhere. This significantly reduces that background broadcast noise, that multi-destination traffic, freeing up bandwidth and making the whole fabric more efficient. It's a really common and important optimization.
That makes a lot of sense. Cut down the chatter. Okay, beyond specific features like ARP suppression, what about general best practices? Things to keep in mind when actually deploying this? Any common gotchas?
Yeah, there are definitely some key best practices, often highlighted by vendors in their design guides.
Like what?
Well, first, route reflectors, RRs. We mentioned EVPN uses BGP. In large IBGP deployments, which EVPN often uses, having every VTTP peer directly with every other VTTP creates a huge mesh of connections. It doesn't scale well from a management perspective.
Right, the n-squared peering problem.
Exactly. So you use route reflectors. VTTPs peer only with the RRs, and the RRs reflect the routes between them. Drastically simplifies the BGP peering configuration and improves scalability. Using RRs is pretty much standard practice.
Okay, use route reflectors. What else?
Next is managing BUM traffic. That stands for broadcast, unknown unicast, and multicast. Even with EVPN learning known unicast destinations, you still have this other traffic.
Right, like ARP requests that can't be suppressed or actual multicast applications.
Exactly. You need strategies to handle this efficiently and avoid flooding it everywhere unnecessarily. This might involve using things like IGMP snooping on the VTEPs to track multicast listeners, or configuring proper multicast routing in the underlay if you have significant multicast sources and receivers. You need to actively manage BUM traffic.
Don't let it overwhelm the network. Makes sense.
Then, of course, security. Basic BGP security practices apply. Use authentication, like MD5 passwords, on your BGP peering sessions. Use ACLs to control which devices are allowed to peer. Don't leave your control plane wide open.
Standard network security hygiene, basically.
Pretty much. And finally, scalability planning. Think ahead. How many VTEPs will you need? How many VNIs? How many MIXI and IP addresses will the control plane need to handle? Choose hardware and design your fabric, including your underlay and your BGP design with RRs, to accommodate not just today's needs, but your projected growth over the next few years. Don't design yourself into a corner.
Plan for growth from day one. Good advice.
And it's probably worth mentioning, too, just briefly, that specific implementations might have their own quirks, right? Like specific hardware needs or maybe features they don't support in the underlay.
That's a fair point. Vendor implementations can differ slightly. For example, some might have specific requirements about the type of routing protocol used in the underlay, or specific hardware ASICs needed for VXLAN performance. Always check the vendor documentation for the specific platform you're using.
Okay. But underlying all of this, the foundation needs to be solid.
Absolutely fundamental. Before you even think about configuring EVPN or VXLAN, your underlay network must be rock solid. Full Layer 3 IP connectivity between all your planned VTAP devices is non-negotiable.
How do you ensure that? Typically, you'll run a standard interior gateway protocol, like OSPF or maybe ICE, within the underlay to provide that robust reachability and fast convergence if links fail. The underlay has to be stable and performant. Also, things like your basic VLANs on the leaf switches, the VTEP IP addresses themselves, loopback interfaces for BGP peering, all that groundwork needs to be meticulously planned and configured before you start building the overlay.
Get the foundation right
Get the
first.
foundation right. Okay. Wow, we've gone from the old days of VLANs and STP limitations all the way through VXLAN encapsulation, the EVPN control plane intelligence, the architecture mobility optimization. It's quite a journey.
It is.
But hopefully you listening now have a much deeper feel for how these modern campus and cloud networks are built, how they handle that massive scale, that constant change, the need for flexibility and mobility.
It's a powerful combination of technologies that really underpins so much of our digital infrastructure now.
So to wrap up, maybe a final thought for our listeners to chew on, something to consider going forward. Okay. Well, think about how things are evolving. Hybrid cloud is huge, right? Workloads moving between on-prem data centers and public clouds, maybe even multiple clouds. There's this increasing need for seamless connectivity, consistent policy, and workload mobility across these really diverse environments.
Yeah, blurring the lines.
Exactly. So how might the core ideas, we've talked about the overlay underlay concept, the control plane intelligence of EVPN, the scalability of VXLAN, how might these continue to evolve? Could they eventually make your local campus, your private data center, and your public cloud resources feel like one single unified network fabric managed consistently? Where could this technology take us next in breaking down those traditional boundaries?
That is a fantastic question. Making it all feel like one seamless entity. Definitely something to mull over as we look at the networks of tomorrow. Thanks for taking this deep dive with us today.